Well, today we're going to destroy buck converters or switching regulators. So why would we do this? Well, we go through a validation procedures on determining how these things function. And with knowing all this, we can make a determination on what we need to include on our design in order to make them better. Let's go ahead and take a look at our victims today. We have these voltage regulators right here, these switching regulators. These are buck converters I got off of Amazon. And for backup, I also got some of these guys. These are as well buck converters, but they're adjustable. Also off of Amazon. And this came in with the pack. Ain't that lovely? So that's one of the ones that I paid for. And they sent this to me. Hopefully these don't turn out bad. I'm thinking they might. Little fake ones. So our first test, we're going to go ahead and take one of these. And we're going to over voltage it. So what the whole intent here is to see what happens when you have a transient event that affects these things. And so what protections you might put in your circuit in order to prevent a transient voltage spike to happen. All right, so we got our first setup here. So putting out 3 volts. I'm going to remove the oscilloscope out of it because I'm going to do an over voltage event on this and see how it reacts. I'm going to also add a load onto this so that way we can see some action. I'm going to add a 330 ohm resistance load onto this, just so that way we can see what happens when we go to an over voltage event or transient voltage. I don't have a proper setup to do an actual transient event, so I'm going to just increase the voltage until something interesting happens. Now, transient voltages are only there for a limited amount of time. You're talking about milliseconds. All right, we can see that there's a load on this, and I'm going to slowly increase this until things blow up. I'll move this back a little bit. So we're at 36 volts. I imagine that's about the limit of the chip. Let me go find my thermal camera. Nice thing about this thermal camera, you can see where the heat's coming from. So you obviously see the heat that's being dissipated by the resistor. So let's go ahead and increase this voltage till it blops. There he goes. Oh, you hear that? So obviously things are a lot hotter than it needs to be. Well, when you do your design, you got to keep into account your transient voltages you might experience. So you can actually add a TVS diode or a snubber filter or even both in order to eliminate this transient voltage spike that might damage your IC. All right, what we're going to do next is we're going to put a reverse polarity on this guy to see how it reacts. So this might happen if you switch your wires and you plug it in the wrong way. Well, let's get this next one set up. Well, this one's broken. Oh, no. That one didn't even come working. Yeah, it's hot in the bottom. It's hot in the bottom. That's number 2 in the graveyard. I got to be careful on my setup because I'm using these alligator clips. I just need to make sure that I have a good connection. I thought this would be easier than constantly going up and redoing everything. Resoldering on for every single one. Let's check this one out. Well, it's pulling current. Well, that's not good. Let's see if I can get this. Oh, come on. What voltage are you reading? So it's reading 4 volts. This isn't what a linear regulator is supposed to look like. Or excuse me, a switch regulator. Let me adjust it to see if it'll fix it. Well, this one's junk as well. Well, guess it's perfect for our next test. What we're going to do here is a reverse polarity check. So I'm going to swap the power and the ground on here, and we're going to see what happens. So we're reading 1 volt right here, and we're reading 3.2 amps, so something's blown. All right, I'm going to swap them back to see if it works or not. All right. Yeah, actually, it went back to working. Not good though, but I'm surprised. These guys actually have reverse polarity protection. Wonder what that dial was on there, but it actually does. Too bad it doesn't put out a good signal like you need it to. This one's garbage. So to my surprise, we actually didn't blow this. Maybe we need to put more current into it. There's different methods and methodologies you can use to actually protect your circuit from an reverse polarity. You can put a diode, you can put a bridge rectifier. You have power losses there, and there's other methods like using a MOSFET or this ideal diode circuit that I got right here on this guy. One of the debates I have with these guys is, do I need to provide short circuit protection when I install a chip on there? It's always a chip. It's always a test that I perform on any voltage regulator or any load regulator to determine its capabilities of limitations. So I'm going to short these guys directly to ground on the output just to see the reaction of the circuit, to see if it's capable of handling a short to power or short to ground situation. So I'm going to take the 2 wires, the positive and the ground rail, short them together. What's this going to do is it's going to test that reaction. So I got 3.9 volts on here. So once I hit this button, it'll short it to ground, and I want to see what the reaction is for it and see if it actually survived this transient response. So as you can see, it does provide a decent response in it. It kicks it short. So as you see on the level, it doesn't go all the way, but it's fluctuating between the two. So it's trying to check to see if it can turn on or off. So every pulse, it's like, can I turn on? No. Can I turn on? No. Can I turn on? No. That's why you see it pulling that current. So it's current pulling 2.6 watts right now. You take a look at what the multimeter says, kind of what the oscilloscope says as well. So once I hit that button, it fluctuates. So it has pretty good response for short to ground. So I was building this. Would I put short to ground protection for this voltage regulator, this switch regulator? No, I wouldn't actually, because it has pretty good response. Now I've pushed and I've held it down, and it hasn't done anything. Let's add a load to see what it does when I actually put a load on there. So reaction is the same. As we saw in the oscilloscope, and when we applied that button, we kept pressing it, it responded pretty well. So that let me know that this circuit or this IC chip is capable of handling a short to ground situation. So when I go through and I design something that has this chip, I can have confidence that when it's short to ground like that, when I take the output of the power on this regulator and short it directly to ground, it can survive that event. And so that provides less worry on me if that's a protection that I have to have, because it already performs that. This next one, we're going to go ahead and take a motor. So this has a high inductive load that has a pretty big kickback or back EMF that is fed back through the circuit, that it causes really high voltage spikes as well as voltage drops. So how does this circuit handle these guys right here? Okay, let's get our next victim all set up. All right, what we're going to do is we're going to put a load on this. I got this little motor right here that's destroyed plenty of regulators, or excuse me, switch regulators. We're going to see how this guy can handle it. So I got it connected up. It's putting out 4.2 volts. It's not a clean signal to see what exactly going on with these. I'm going to turn this off. This is about the ugliest signal I've seen from a voltage regulator ever. Maybe it's because I'm using these banana clips and might have bad connection. There it goes. Oh, let's try the auto set, see if that gives us something to look at. Well, there it goes. Not sure if that was me or if that was the actual switch. But I turned up the voltage to 7.5 and then it stopped. So I didn't survive that. So when you take account these regulators, you got to take account what kind of load you're going to put on this. I'd never actually recommend putting a motor onto one of these. I mean, you have different devices, motor chips, ICs that are made specifically to run motors, so that way you don't have an issue. So you keep account onto your load that you're putting on it and provide proper filtering as well as protection for that. Like I could have put a suppressor diode on here that prevented what happened with this IC chip. So it's just another thing you got to keep in mind, what type of load you're going to put on there and what's the best solution for that load. So I don't think it's proper for a voltage regulator to run a motor. One thing you always have to do with your regulators is to find out its limitations as far as its load capabilities. These guys are rated at 3 amps, but do you think they're going to be able to handle 3 amps? All right, now I put a load on here. So this is supposed to be 2.5 amps. Let's see how this thing handles it. You can definitely see on this regulator, on the switching regulator, where it's switching. So that's one issue with these switching regulators. As they switch on and off, they'll do this. Now this one's looks like it's cycling off and on. It might be overheating. So these, according to the data sheet, were rated at 3 amps. So we're at 2.5 right here because I have 6 resistors in series. All right, so yeah, this is where I'm starting to see it overheat. So I'm showing 100 degrees C on this regulator. Oh, this bad boy's getting hot now. And so overloading the circuit told us a few things. One, thermal regulation is going to end up kicking in, and it's going to end up reducing your voltage. Also, you saw on the oscilloscope, these guys can't handle really that much voltage going through them. Or excuse me, these guys can't handle that much current going through them, even though they're rated at this. My suspicions are these chips aren't real, and they have a hard time handling those loads when you put it on there. That's why you saw a waveform pattern. One other thing that I made by observers is your capacitors. So this is the proper size capacitor for this chip. You don't see that on there. There's not a load capacitance in there. I imagine if they put the proper load capacitance on here, it will clean up a lot of the issues that we had. Not all of them. Now I just want to show real quick, when you have a properly designed regulator, this is kind of what it should look like, at least the switch buck converter. So there's not a whole lot you can see on there. There's a little bit, but you know, it works correctly. It's not like the other ones that we saw where it was all over the place. So after all this, we went through, and what did I learn? What did we learn? You know, I went through and I tested my design as well with the same things. So this already has reverse polarity. It has high voltage transients protection on here. It has a TVS diode that prevents over 100 volts going through it. And one thing I didn't take into account was thermal regulation, and also going to compact and tighten this guy a lot up. So applying some thermal vias onto my design will make this guy be able to function better. One other thing I learned as far as limitation is once this gets up to about 1.8 amps, it starts to down regulate the current output. So it does this by reducing the voltage. So now I know there's this limitation on here that I have to take account for. Do I think I'm going to be pulling 2 amps out of both of these? No. But, you know, all this work, we learned a lot about the limitations of our circuits, and it will help make our design better. So if you like the content, hit a like. If you want to see more videos, subscribe, and thank you for tuning in.